Thank you, and thanks to the organizers for the invitation. I'll be reporting on some work with Florent Hivert, and as the title indicates, this is going to be about so-called Okada algebras. And so I'd like to just tell you what these are briefly, and a little bit about their representation theory, and then tie that story in with Stanley's famous Young-Fibonacci lattice, and talk about its combinatorics, and then finally from there go into this diagrammatic realization of the Okada algebra. So the Okada algebras. So this is the nth Okada algebra. It's an associative unital algebra with n-1 generators, and it has a kind of Coxeter style presentation, which depends on two sets of parameters. So there's a set of x parameters and y parameters, which I'll take to be complex numbers here. And so there are three kinds of relations. And so Okada showed when he introduced this algebra that in fact this algebra is finite dimensional and has dimension n factorial, and that for generic values of these parameters, this algebra will be semi-simple. And moreover, up to isomorphism, these parameters can be, the y parameters can be taken to be 1 when in the semi-simple case. And in fact, that's for today. I'll just restrict to the situation when the y's are 1, just for ease of presentation. Although my results with Florent work for general parameters. So a little bit about the representation theory. In this semi-simple case, the irreducible representations, or the isoclasses of the irreducible representations, they're indexed by what are called Fibonacci sets of rank n, here on the right-hand side. And what these are subsets W taken from 1 through n, such that the cardinality of the set has the same parity as n. And if I order the set, from smallest to largest, and take the rth element, then it has the same parity as R for every R. And if you think about it for a little bit, you realize that the number of size of the collection of all such rank n Fibonacci sets is exactly the nth Fibonacci number. So hence the adjective. So if you believe this bijection, then if I take such a Fibonacci set, then I can construct some representation, some irreducible representation of the nth Okada algebra. And the n-1st Okada algebra naturally sits inside of the nth as a subalgebra. So I can play the restriction game. I can restrict this representation down to the subalgebra. Of course, when I do that, I'm going to get a representation which is reducible. And the irreducibles that show up, they will, the irreducibles from Fn-1 that show up in this decomposition, they either show up with multiplicity exactly 1 or 0. So it's multiplicity free. And the ones that do show up, the Fibonacci sets that index them, they are covered by W, where this covering relation it comes from some what's called the Young-Fibonacci partial order, which is some partial order that you can introduce on the set of all Fibonacci sets of all ranks. So I'm taking this is now an infinite set, and in the next slide here, I've drawn the Hasse diagram, or part of the Hasse diagram. So this is Fibonacci sets up to rank 5. So starting at the very top, we have the unique Fibonacci set of rank 0, which is the empty set. And then level by level, we have the corresponding rank R Fibonacci sets. So at the very bottom here, I have the Fibonacci sets of rank 5. There are 8 of them, as there should be. You'll notice in this picture that there are some repetitions, right? Like, for example, the empty set is repeated. That's because, for example, the empty set is a Fibonacci set for every n when n is even. So if I were to be very meticulous here, I should, every Fibonacci set should be, I should put a subscript on every set to indicate, what rank I'm considering it. So it's sort of 2 pieces of information. It's the set and the rank, so that I can distinguish these different empty sets, for example. And then the covering relations are easy enough. So U is covered by W if either I can get U by taking W and removing its maximal element, or the reverse. I get W by taking U and removing its maximal. And okay, these covering relations extend transitively to a full partial order on all of these sets. And with respect to this partial order, we get a ranked lattice. And it's a ranked lattice, which is also what's called one differential. So I don't want to go into the details of what this means, except to say that other than the lattice of integer partitions, this is the only other one differential lattice that exists. The important property, or let's put it this way, a consequence of being one differential, is that whenever I have a poset, which is one differential, it supports a version of the Robinson-Schensted correspondence. And which means concretely that there will be, for every a bijection between permutations in N, and pairs of saturated chains in the poset, which begin at the minimal element and have a common endpoint at some level, at some point in rank level N. And indeed, in the case of the Fibonacci lattice, this was studied by Fomin, and Sergei Fomin, and he gave such a...
Jeanne, just
Yes?
a reminder that there's only like 3 minutes left of the talk in case you have several slides you want to get through.
So yes. Anyways, so we make use of this. In what we do, we make a kind of graphical version of this bijection. And finally, so what is the main result? So let me explain what an Okada arc diagram is. It's a picture of a perfect matching where I have n vertices on the left and another n vertices on the right of a rectangle. And I join them or match them by arcs, which should be non-crossing. And in addition to that, I label them with integers that we call these H labels. And if I have an arc which joins vertices I and j, its H label has to be at least 1, integer which is at least 1, and which at the same time should be bounded by the min of the endpoints. It should be, this H value should have the same parity as this min. And then finally, whenever I have whenever an arc beta is nested by an arc alpha, then the H label of alpha is strictly smaller than the H label of beta. So here I've indicated 2 examples of these kinds of pictures. So these are the kind of pictures that you see showing up in the Temperley-Lieb algebra, except they're carrying this extra data of H labels. And as usual, I mean, you can compose these things. So if I have 2 Okada arc diagrams, then I can concatenate them. And when I do this, I read the result up to isotopy. And I also, whenever I see a loop, when I do this concatenation, I might create a loop and I extract this loop, but I remember the loop by multiplying in by an Okada parameter, one of these X parameters, where the index of the parameter is the min of the H labels of the loop that form from the corresponding loop. And the H labels of all of the arcs are just the mins of the arc fragments that form them in the composition, in the concatenation. So this defines a product on the vector space of all diagrams. So if I take two Okada arc diagrams and I do this concatenation, the result is still an Okada arc diagram. And then the main result is that that the map that sends an Okada generator EI to script EI defines an algebra isomorphism from the Okada algebra to this algebra of arc diagrams with this composition, where the script I is this kind of elementary Okada arc diagram, which I've depicted here. And since I am out of time, let me just end there.